Welcome back to McMaster University course Computing and Software 701 Logic and Discrete Mathematics. My name is Bill Farmer. We're going to be looking at a new topic, simple type theory. Here's an outline for what we'll be doing. We're going to talk about what is simple type theory. Then we're going to look at the syntax and semantics of a version of simple type theory called Alonzo. Then we're going to look at different operators that we can define in Alonzo. We'll move on to full Alonzo, an expanded form of Alonzo. Then we will discuss a series of examples that show the expressivity of full Alonzo. And finally, we will conclude with a proof system for Alonzo and a series of remarks about Alonzo. Okay, so what is simple type theory? In my opinion, simple type theory is a simple, elegant, highly expressive, and practical logic. Unfortunately, this is a logic that, although a few computer scientists know about it, basically the rest of the mathematical world knows nothing about it. It is a logic that mathematicians and engineers and scientists are not familiar with. It is nevertheless the most popular form of simple type theory. However, today, another version of, the most popular form of type theory, another version of type theory, dependent type theory, is becoming increasingly popular today in the computing world. So, as a type theory, types are used to classify terms as value. So if we have a expression, and that expression will have a type, and that type will tell us something about the value. So, for instance, if the type is a natural number, we know its value will be a natural number. And types are also used to control the formation of expressions. This is analogous to how types are used in programming languages to prevent type errors. Now, this form of type theory, simple type theory, is non-constructive and two-valued. So it's a completely classical kind of logic. It is higher order in the sense that quantification is over functions, and it can be viewed as a function theory. So this is often of interest to people who do functional programming, because in many ways, simple type theory can be viewed as the underlying logic for many functional programming languages. Now, it is a natural extension of first-order logic. In a sense, we're adding more machinery to first-order logic. It's based on the same principles as first-order logic, and it includes not only first-order logic, but second-order logic, third-order logic. It includes nth-order logic for all n. In 1908, Bertrand Russell proposed something which he called the theory of types. Today we call this the ramified theory of types. So his theory of types was a logic that was designed to prevent the set theoretic and semantic paradoxes that people, including Russell, had discovered around the turn of the century from the 1800s to the 1900s. And these paradoxes were very worrisome to people concerned about the validity of mathematical reasoning. And not only that, Russell and Whitehead tried to show that mathematics can be reduced to logic. So they used the theory of types as a logic to develop as their goal, develop basically all mathematics. And this produced a work called Principia Mathematica. So this was one of the really first formalizations of mathematical knowledge, and it was done using the theory of types. Now, the type part of this logic was rather complicated, and Trzestek and Ramsey in the 1920s they propose a simplified version of this ramified theory of types, which was called the simple theory of types, or just simple type theory. And later, in the 20s and 30s, various people, Carnap, Gödel, Tarski, Quine, they presented detailed versions of simple type theory. And then in 1940, Church presented another version of simple type theory with lambda notation built in. And this has proved to be very influential. In many ways, this is the start of type theory in computing. So the use of type theory in computing can pretty much be all traced back to Church's work in 1940. Now, one of the reasons that many people did not like simple type theory is because it did not have a sound and complete proof system. But Henkin showed in 1950 that if you use a different semantics than the standard semantics, you could develop a sound and complete proof system. So this was a major result for simple type theory. And then in 1963, Henkin and Andrews, and by the way, Henkin and Andrews were both students of Church. Henkin and Andrews produced a beautifully concise formulation of Church's type theory, Church's system, based on just equality. And then in the 80s and 90s, people started designing and building high-order theorem proving systems, higher-order proof assistants, and these were, by and large, based on simple type theory. So the question is, who needs simple type theory? So my claim is that understanding simple type theory would be beneficial to anyone who needs to work with or apply mathematical logic. So this is particularly true for engineers who need to read and write precise specifications, computer scientists who employ functional programming languages like Haskell, Lisp, and ML, software engineers who are going to be using higher-order proof assistants to model and analyze software systems, and finally, mathematics students who are studying the foundations of mathematics or model theory. Now, there have been a number of proof assistants based on simple type theory that I mentioned. These systems were pretty much developed in the late 80s, early 90s. I want to point out one system here called IMPS. This was developed by myself and my colleagues Joshua Gutman, Javier Thayer at the MITRE Corporation. And it was released in 1993. And it's notable because unlike these other systems, it can handle undefined expressions in a direct way. So I am proposing a version of simple type theory named in honor of Alonzo Church called Alonzo. Now it is based on Church's type theory. The version I told you about that Church introduced in 1940. And this version of type theory, as I said, had lambda notation. So Alonzo is based on Church's type theory, but unlike most versions of predicate logic, including Church's type theory, it omits undefined expressions. So what that means is, in Alonzo, you can write down this expression, and its meaning is undefined, which means it doesn't denote anything. It has no meaning. And this is the way things are normally done in mathematical practice. You know, another example is square root of minus 2 when the square root is on the real numbers. So this is a perfectly good expression. It just doesn't denote anything. So Alonzo omits undefined expressions in this fashion, and that sets it apart from other systems. Now there are two versions of Alonzo. The first version is Core Alonzo. This is a minimal version of Church's type theory based on just equality, function application, and function abstraction. It's a very nice logic to study. It is not so practical. The other version is full logic, full Alonzo. It is a practical version of Church's type theory, and it's extended with machinery for definite descriptions, sets, tuples, and lists. Okay, so what's the purpose of this presentation? Well, it's multifold. The first is to present simple type theory, but do that using Alonzo. The second is to show the virtues of simple type theory. As I've mentioned, simple type theory is much more practical than first-order logic, but it's not well known. It's not well known outside of computing. The third is to argue that simple type theory should be an attractive alternative to first-order logic for practical-minded scientists, engineers, and mathematicians. Now, the presentation will be based on 2 works: this journal paper, The 7 Virtues of Simple Type Theory, and this textbook, Simple Type Theory, A Practical Logic for Mathematics, Computing, Engineering, and Science. The textbook is only partially written, but it covers most of what we're going to be discussing in this course. Now, I want to mention, in the textbook, there's 2 kinds of notation that are used. There's an official notation and a compact notation. The official notation is more suitable for writing software that manipulates Alonzo expressions. The compact notation is closer to what people would normally use for, and it's compact. In our presentation, we're going to focus, or we're going to use the compact notation. Okay, so that completes our lecture for today. The next lecture will be on the syntax of core Alonzo, and I'm going to stop here, and I wish all of you a good day.